First of all, we must make the difference between shortest path problems and path-finding problems. As you can see here on the right, the path-finding problems are quite more complex than the shortest path problem because you have a lot of degrees of freedom to find the route from an origin to a target. But this problem that deals with motion planning when you are dealing with mobile robots can be simplified if you add a grid on the problem. A grid with some nodes, as you can see here, and edges, as you have here. This is what it's called a grid-based search. If you don't do that, you have a lot of degrees of freedom. So this leads us to this kind of problems, the shortest path problems, where you have an origin, when you have a target, and then you have a list of nodes, as you can see here, and then you have the edges that connect one node with its neighbors. As you can see here, sometimes these shortest path problems, they don't have any information on the edges, but sometimes there is some information on the edges. This, we will see later on, is what we call the weights. These weights will lead us to the total cost of the path we choose of going from the origin to the target. So what do we want is to get the minimum cost path from the origin to the target. So we want that the sum of all the total weights of our path to be as minimum as possible. So first of all, we will have a look at these edge costs. So these weights, as you can see here on the top of the figure, here you have the weight of going from A to B. And as you can see here, this is a directed graph because you can go from A to B, but you cannot go back. But at the bottom, you can see here that we have a cost that is associated to the cost of going from A to B, but then you can go back with not necessarily the same cost. You can have a different cost. For example, let's say that here we have A and here we have B, and we want to go from here and climb up this slope and reach our destination, B. As you can see here, it costs a lot to climb up this slope, but it's cheaper in terms of, for example, energy, fuel consumption, time, to go down from B to A. So that's the idea behind the costs. These costs can be fuel, distance, that is the most typical distance, time, any combination of these variables. So it's like a measure on how much it costs from going from A to B. So then when we have a digraph, as you can see here, that it's a directed graph, you can see the arrows, you can go from 1 to 2, but you cannot go from 2 to 1. So it's a directed graph. This graph leads us to what we call an adjacency matrix or adjacency list. As you can see here, we have here the origins, and here we have the destinations. As you can see, the cost of going from 1 to 1 is 0. So that's why here we have this symbol. But the cost of going from 1 to 2 is 1. So the cost of going from 1 here to 2 is 1. But as you can see, you cannot go back. So the cost of going from 2 to 1 is not 0, but infinitum, because there is no connection between 2 and 1. Then we can have a look, for example, at the cost of going from 2 to 3. As you can see, here we have this arrow, and it tells us that it has an associated weight of 3. Here we are. But we cannot go back. This is not possible. So that's why here the cost of going from 3 to 2, it's also an infinitum. So the symbol this in the figure is equivalent to 0 in the matrix diagonal and equal to infinity outside the diagonal. Here you have another example with the only difference that now you cannot go from 3 to 4 like this, but here it's possible to go from 4 to 3. Here, this example is only for checking. You can stop the video and check that you are able to get this adjacency matrix from this diagram. Pay attention that here the connection between 2 and 1 is double. You can go from 2 to 1 and from 1 to 2. So that's why here in a symmetric form in the matrix you have a number 8 in here. The same goes from 2 to 5. Here we have this, and here we have this. Let's have a look on how many algorithms there are in there. Well, there are a lot of algorithms, but here in this course we only will be focused on 5 methods. First of all, we will study the uninformed methods. These uninformed methods are methods where the edges between two neighbors, they have no information. And we don't have any information on how far is every node from the target, from the final destination. So these methods are called blind methods or brute force methods. And these methods are used, for example, in order to get out of a maze. The two methods that we are going to have a look are the breadth first search algorithm and the depth first search algorithms. Then afterwards I'm gonna make the difference between them. Then we have the informed methods. The informed methods will be the greedy, the Dijkstra algorithm, and the A-star algorithm. These methods, far from the previous ones, the uninformed, they give us some information on, for example, first of all, how much it costs from going here, from here to there. So what's the cost between two neighbor nodes? And then we may also have the information on how far is this node from the destination and how far is this node from the destination. I will define this kind of information later on. All the codes that I'm going to use in this presentation belong to this author that is a lecturer in Pakistan. Let's have a look at this example. As you can see here, we have 5 nodes from A to E. So these are the origins and these are the destinations within the adjacency matrix. As you can see, when there is no connection, we have an infinity. And when you want to go from one node to the same node, we have a 0. Let's have a look at first on what's the difference between the breadth first search and the depth first search. Let's have a look at these 3. As you can see, we have the root, that is A, and then we have all the branches in these 3. Well, first of all, the breadth first search works. First of all, we know that it's an uninformed method because, as you can see here, we have no information on how it costs. Okay, what's the cost of going from A to B, A to C, and so on. We don't have this information. So the breadth first search works as follows. We start here at the root of the tree, and then we assess all the sons of this root. So we have B and C. As you can see here, we have A, B, and C. After that, we have a look at all the sub-branches of the first element in the second level. As you can see here, we have the first level, then we have the second level, and the third level. So the breadth first search, in comparison with the depth first search, is going as follows. First of all, it assesses all the elements within a level. So the breadth first search is not going down to the next level if it hasn't achieved all the elements in the actual level yet. So that's why the first element is A, and then comes B, and after B comes C, because there are still some nodes in this second level, as you can see. Afterwards, once the method has finished with all the elements in the second level, goes to the third. And the third begins with D, and then E and F. E and F. As you can see here, the depth first search works quite different. As you can see, it starts with A, and then the next is B. Why? Because there is no one else in the first level. So then this depth first search goes to the next level, B. Afterwards, as you can see here, B has a connection with the third level. So that's why the next node that will be explored will be D, because the breadth first search works this way. The first level, the second level, the third level, and so on. While the depth first search works this, through all the levels, then through all the levels, through all the levels, and so on. So breadth, depth. So as you can see here, we have A, B, C. We have reached the last level. So then we go back. As you can see here, there are no connections between B and another nodes. So then we go back again with A, and then goes A, C, E. So A, C, and E, and finally we go back and we explore F. As you can see, there is only a difference between here we have C and D, but here we have D and C. And the difference is because the depth works this until it reaches the end. And then it goes back and reaches the end. And then it goes back and is going through all the levels. If we apply this with our example, it will be the following. As you can see here, we have the root, that it's A. So first of all, we will apply the breadth, as you can see here in yellow. So this is the root, and then we will check all the elements that depend or are connected with this root. As you can see here, we have 3, B, C, and D. So that's why here we have A, B, C, and D. And finally, once we have finished, this would be the first level, this would be the second level, and this is the third level, as before. So that's the breadth first search. But what about the depth first search? It will be the following. We begin with A, then we continue with B, then C, and then E. So that's why here we have A, B, C, and E. Once we have finished, we go back, and as you can see, we have A, D, and E that is also the same. So that's why it's A, B, C, E, and finally the D. That was the single unexplored node. While the breadth first search was A, B, C, D, and E. So that two nodes are exchanged. Let's have a look now at the informed methods. First of all, the most simple information that we can have on a digraph is the heuristics. The heuristics is like the rule of thumb. What do I mean? It's like a measure. It's an under consideration of the measure on how it goes of going directly from every node in the diagram to our destination, that it's E. This is the origin and this is the target. So it's like the length, like the distance that exists between the actual node or the node that is considered to the target if you could fly, for example. The Euclidean distance. The Euclidean distance from one point to another is the straight line that connects both nodes. In opposition to that, we have the Manhattan distance. This kind of distance is like if you were on the square streets within a city. So, in opposition to the Euclidean distance, that is the straight line, the Manhattan distance means to go straight, then turn 90 degrees. So, this A, B. So, the addition of A plus B, A plus B, is the Manhattan distance, while this is the Euclidean distance. Depending on the problem, you can use, or maybe you are forced to use, the Euclidean or the Manhattan. It could be, for example, when you have some constraints on your movement. If you can only move, for example, this and this, so you can do only straight, so go up, down, right, and left movements, for example, you may use the Manhattan distance in order to guess the distance to the destination. But you can have also the Euclidean distance as a rule of thumb on the estimation on the target. So let's go again to the example. As you can see here, I have written down all the measures. Here you have 2.5, 2.5. 2.5 is the distance from this point to this point, this point to this point, but we are not going to use the Manhattan distance. We will use the Euclidean distance. So as you can see here, here we have a 1.5 and here we have a 3. So the heuristics list is the following. The cost of going from A to E is 6 as an heuristic measure, because that measures 3 and this measures 3. Pay attention. The heuristics has nothing to do on the cost, the real cost of going from A to C. The heuristics is an underestimation on how it costs. The cost of going from A to E, from the origin to the target, from B to E, from the actual node to the target. Let's have a look, for example, at B. B, here we have a 5. Why? Because we have this distance. It's the Euclidean distance. We have 2.5 and 2.5, so that's the reason of this 5. Let's have a look, for example, at D. Here we have D equal to 3 because here we have 1.5 and 1.5. And obviously here E, as you can see here, E is 0 because the distance of E from E is 0. And finally, C, the cost of going from C to E, but has an heuristic measure, nothing to do with the weight. It's only a guess, it's only a rule of thumb, is a 3. In this case, here we have a coincidence. Here we have a 3, but you must not confuse both terms. They are different. So what about the greedy algorithm? The greedy algorithm will start at the origin and will reach the target. Here it will reach the target, but by only following all the nodes that are connected with the actual node, that they have the minimum heuristic value. Let's have a look. We have this node. This node has 3 neighbors. 1, 2, and 3 neighbors. Why? Because there is a connection between A and these nodes, as you can see here. Okay? But what's the heuristic of B? The heuristic of B is 5, because here we have a length of 5. The heuristic of C is 3, because 3 has a heuristics of 3 from E. And finally, we have D, and D has also heuristics of 3, because it's 1.5 plus 1.5. So at the end, we have a tie, because here is a 5, here is a 3, and a 3. So we can decide about C or D, either. So let's suppose that we decide for C. So then we check again, but C has only a single neighbor. That is our destination, our target. So that's why here we have A, C, and E as the solution. But it could be acceptable the same, A, D, and E. As you can see here, the cost of going from A to E but passing through C has a cost of 11, while A, D, and E has a total cost of 6. So this tie allows us to choose any of these routes, but obviously they could be weighted so different. So that's how it works, the greedy algorithm. Let's go now for the Dijkstra algorithm. The Dijkstra algorithm is quite different because the Dijkstra algorithm is not using the heuristics. It's only using the weight that is associated for every edge in the diagram. So first of all, we are here, as you can see, we are here in A, and we assess all the neighbors of A that are B, C, and E, here in light green. As you can see, the smallest cost is 2, so here we decide in dark green for B. Afterwards, this method reconsiders the unvisited nodes. So as you can see here, the only neighbor of B is C, but you can reach C from A or from V. And as you can see here, D remains being considered as a candidate. That's the tip for the Dijkstra method. This method does not forget about these unvisited nodes. It still considers these previous neighbors. So here we have a 5, 6, and 8. So obviously we decide about 5. So we forget about B and now we consider D with a total cost of 5. Finally, let's check all the neighbors. As you may remember, we have a 6, we have an 8. These are already visited nodes, so we are now considering the neighbors of these already visited nodes. As you can see here, we have 6, 8, and 6, so we have a tie with this 6 and this 6. But we will decide for E because it's the target, and I'm glad and so happy to reach the target. So that's why the final route will be this and this, and the waypoints will be A, D, and E. As you can see here, this method doesn't allow any confusion. It's optimal because we have reached the minimum cost, as you can see here. So this method is optimal. But if this method has a lot of nodes, it takes a computational time that it's so long. So we have like a mixture of the previous two methods, the A-star algorithm. The A-star is like if you use the greedy plus the Dijkstra method. This is the A-star, because the A-star uses not only the weights of every edge, but also the heuristics list. So let's have a look on how it works. Here in the nodes, I have written in green the heuristics for every node. As you can see here, we have a 3, 3, 5, 6, and obviously 0 because E is the target again. First of all, we begin with A, and we consider the nodes. But now, these nodes B, C, and D that are the neighbors of A, we assess them not only by the weight, not only by the heuristics, but the addition of these two numbers. So we will add 2 plus 5, and this is 7. What about this 11? It's 8, that is the cost of going from A to C, plus the heuristics of C, that is 3. Finally, for D is 5 plus the heuristics of D, 3, equals to 8. So we obviously decide about B, because 7 is smaller than 8 or 11. So then we decide about B, so we visit B and we consider now the neighbors. Again, in the same way that the Dijkstra algorithm, but now, in addition, we have the heuristics as an information for the method. So here we had the 11, you remember from the previous step, but now we can reach C not only by A, but also by B. So that's why we have 6 plus 3 equals to 9. The 3 comes from the heuristics, and this 6 comes from 2 plus 4. As you can see, the 5 of the heuristics of B has not been added, because this method works as follows. You add the heuristics of the node that is being assessed, in this case is C, and the heuristics is 3, and you add this number to the total cost, the total effective cost of going from the origin to this node. And the effective cost is 2 plus 4. 5, the heuristics of B, has nothing to do on that. So that's why we have now 8, 11, and now additionally we have a 9. So we decide obviously for 8, because it's the minimum number, and then finally we have the following. We assess again the C, because it's an unvisited node, it's a neighbor, and finally E. And as you can see here, E has a total cost of 5 plus 1 is this 6, and finally plus 0, because the heuristic cost from E to E is 0. So here we have a 6. And as you can see here, now we don't have a tie, like in the Dijkstra method. Clearly, the path is A, D, and E. And as a final consideration, you can say that the method, the A star, has reached, obviously, the same path as Dijkstra. That doesn't happen always. But the important thing of the A star is that when you have a lot of nodes in the diagram, it saves a lot of time, a lot of computational time, because the heuristics, the use of the heuristics in the formula allows you to go to those nodes that leads you to the destination. Let's suppose that here we have a lot of nodes next to A, but these nodes are neighbors to A, but these nodes are not in the direction of our destination, of our target. So these nodes will be discarded by the A star method because the heuristics increases, while in this direction the heuristics decreases. And the Dijkstra algorithm, because it's not using these heuristics, will run slower than this method. Obviously, in some way, the A star algorithm is quite optimal, not strictly optimal, because you are not assessing all the neighbors all the candidates like the Dijkstra method does.